The last type of special graphing thing that we're going to look at is graphing absolute value functions. Now, you've graphed the absolute value of x before, and in grade 11 you graphed the absolute values of parabolas. And now in grade 12 we can graph the absolute value of any function. So what does that do? Well, we do the same thing as far as writing out steps from before. Number one, you're going to graph f of x first. Oh, first d. Y equals f of x first. So you graph the inside function first. And then two, let's see what best way to write this. Where the graph is below the x-axis. That is wherever you have negative y values. What does an absolute value do to negative values? Makes them positive. So wherever the graph is below the x-axis, you will have your y values be negative. What you're going to do is you're going to make them positive. And you do that by flipping it over the x-axis. What happens then is the entire graph becomes above the x-axis, making all of your y values positive. So now we have some options for graphing something like this. You want to graph y equals the absolute value of 2x plus 3. This could be one we could do with our basic transformations, but now it might even be easier to use this new technique, which is also the same technique that you looked at in grade 11. So in grade 11, if I graphed 2x plus 3 first, I'd have a y-intercept of 3, a slope of 2. I would have an x-intercept of negative 1.5, 0. Then right beside it here, if I want to graph the absolute value of that function, I need to take wherever it's below the x-axis, this section right here, where it's below the x-axis and your y values are negative, and they get flipped up over the x-axis. So the parts, negative 1.5, 0, oops, 0, 3, the parts that were positive, this whole section stays exactly the same. And that yellow section where it was negative gets flipped up over the x-axis. And if you wanted to, you could take a point like negative 2, negative 1, and say my y value is going to become positive. So now I have negative 2, positive 1. So we can take specific points and change the y values to be positive. Or what we can do is just flip that section up over. I think this is an easier method than using transformations. If you wanted to do transformations in this equation, absolute value of 2x plus 3, well, your parent graph would be the absolute value of x. What does the 2 do? Horizontal compression. You'd multiply all of your x values by a half. What does the 3 do? Okay, you want to say 3 to the left, but we have to write it in factored form first. So if you wanted to do transformations, you would first have to factor out the 2, do a horizontal compression by a half, making it narrower, and then translate it 1.5 to the left, or 3/2 to the left, and we would get the exact same graph. However, in this situation, I think it's much easier just to graph the line and flip the negative part up. Here we're given the graph of a cubic, and it's already been factored for us. Had it not been factored for us, you could have graphed this by saying, I know that my x-intercepts are at -3, they're at 0, and at +2. I know that this, if I expand it, makes a positive x cubed graph whose end behavior acts like a line, starting in the bottom left and rising to the top right. So you could have drawn a sketch of this graph just given the equation. We want to graph the absolute value of f of x. Again, what's going to happen is all of the sections that are below, they're going to get flipped up. All of the sections that are above, so this, oops, I want to go blue. This section and this section will stay the same. But this section will get reflected up, and this section will get reflected up. So our final graph looks like a bunch of bumps, but all that's happened is those yellow sections have been reflected over the x-axis. What's that?
If they don't ask for like specific points, could you just reflect it by
By estimation? Yeah, that's what I've done here. And so remember, when you graph your cubic functions, do we have to find these maximums and minimums? No. Right? We're leaving that for next year for calculus. But now, so wherever you estimated it, showing that flip over is what it would be in the end. Okay? And then what can happen is sometimes in our last example, sometimes we can combine transformations with absolute value functions with further transformations. So what would that look like? So we're going to end by graphing. Wow, that doesn't look like a P. We're going to graph y equals the absolute value of the square root of x minus 2 minus 1. So this is going to combine what we've learned in transformations with what we learned with absolute values. Is this going to get you through the day? Okay, good. Just checking. So what did we do with absolute value functions? We graphed the inside first and then flipped what was below above. What does that minus 1 do at the end? That's a translation down 1. So now we have to decide, how do we put these things together? How do we do this absolute value and the translation together? Okay? When you look at this, does it make sense that this graph gets translated down 1? So what we're going to do is we're going to graph that absolute value of x minus 2, square root of x minus 2 first, get that graph, and then take that whole graph and move it down 1. So when you're combining things like this, you sort of have to think through it logically and say, well, what all needs to happen here? I can see that minus 1 is going to be a translation down. I can see that that would be the last thing that I would do. So before I translate it down, I need to graph that first part. How do I graph that first part? Well, it's an absolute value. I graph the inside first, and then I flip whatever's below. So we're going to start with just graphing the inside. What does the square root of x minus 2 look like? That's my square root graph moved down 2. So my square root graph normally has 0, 0. It now has negative 2 comma 0. It normally had 1 comma 1. It now has 1 comma negative 1. And has 4 comma 0. So I took my square root graph and I just moved it down 2 units. Yes? Yes, it would be 0, negative 2. Thank you. So now, when we look at what does the absolute value of the square root of x minus 2 look like? Well, we have only one section here where it's negative, right here. That section is going to get flipped up over the x-axis. So instead of 0 comma negative 2, we'll have 0 comma positive 2. Instead of 1 comma negative 1, we'll have 1 comma 1. And we'll still have 4 comma 0. So your graph you get some kind of interesting looking points because when it flips over, it's no longer smooth. It's kind of got a bump at that point. So the yellow part got flipped up, and then the green part stayed the same. And now we can do the final graph, absolute value of square root of x minus 2, which is that graph, minus 1, which would shift it down 1. So we can take all the points that we have, right? 0 comma 2 shifted down 1 would become 0 comma 1. 1 comma 1 shifted down would become 1 comma 0. And 4 comma 0 shifted down would become 4 comma negative 1. Still has that weird kind of bounce at that point. And this would be our final graph. What's that? You keep the negative. And that's why I wanted to show you this example, because it had an absolute value in the original question, but in the end there's some negative values, which should make sense because what are we doing at the end? We're subtracting 1. So if the last thing you do is subtract 1, it is possible to go into the negatives. Does that make sense? Okay? But for whatever reason, when this comes up on an exam, everybody freaks out because they're like, I saw an absolute value, and so you get some extra flipping happening. We don't have to do any extra flipping. This is just the final graph.